Hello, everyone, and welcome to the lecture video on Chapter 5, Stereochemistry, Part 2. All right, so in Part 2, we're starting at Section 5.3, which is called Designating R versus S Configuration. So hopefully by now you've convinced yourself that molecules like the two on the screen below are different compounds, and they're related as enantiomers. But if they're different compounds, then they can't have the same name. So for example, this group attached to a butane would be called 2-chlorobutane. And if this is called 2-chlorobutane, then this can't also be called 2-chlorobutane because they're different compounds. But in fact, they're both 2-chlorobutane. So how can you differentiate them in terms of their name? Well, what you can do is use what we call the Kohn-Ingold Prelog system to designate each chiral center as either having the R configuration or the S configuration. So for example, because there's one chiral center in the molecules above, and those two compounds are related as enantiomers, then one should be R and the other one should be S. And if we add that to the name, then we will have distinguished them. One will be called R2-chlorobutane, and the other will be called S2-chlorobutane. So we have to learn the rules of how do we figure out if the chiral center is R or S. So to figure out if a chiral center is R or S, we use a stepwise procedure. First, we identify the chirality center, specifically the carbon with the 4 different groups attached. And then we prioritize those 4 groups attached to that usually carbon chiral center. We prioritize them 1, 2, 3, and 4. And the prioritization is based on the atomic number of the atom attached to the carbon. And then once we have our 4 priorities, we want to arrange the molecule in space so that the lowest priority group faces away from us. And then count the group priorities 1 to 2 to 3 to determine whether the order progresses in a clockwise or counterclockwise direction. If it progresses in a clockwise direction, we're going to call that R, and counterclockwise is S. And again, a handheld model, particularly at first, is a very useful visual aid for this process. So let's look at how we would prioritize 4 different groups attached to a carbon. Again, the prioritization is using atomic numbers, which you can find on the periodic table. But the group here with the highest atomic number is chlorine, followed by oxygen, followed by carbon, followed by hydrogen. So they've labeled them 1, 2, 3, and 4. So that was step 1. Step 2 was to arrange the molecule in space so that the lowest priority group faces away from us. And by away from us, we mean that we want the lowest priority group, which is group number 4, to be on the dash. On the dash is away from us because it's behind the plane of the page. So for example, if you have a structure like this, where the 4th priority group is pointing towards you, you can flip the molecule over like a pancake, right? So you take it and you flip it over, and that's where that handheld model is really useful. And then whatever was pointed out at us ends up pointed back when we flip it over, and whatever was pointed back ends up pointed out at us. And the 2 groups in the plane end up switching. But through this rotation, now we have the molecule that we can observe in the correct way, which is with the 4th priority group pointed away from us. By the way, there's another trick besides doing this that can be helpful as well if you have trouble with this sort of rotation. And I'll go over that eventually. Okay, next step though is we need to look at the numbers 1 to 2 to 3, again, ignoring 4. Remember that we have now carefully placed 4 behind. And now we're just looking at the order of progression from 1 to 2 to 3 to determine if it's a clockwise or a counterclockwise rotation. If it was a counterclockwise rotation, like in this example, then we call this chiral center S. So we just determined that this carbon, which is a chirality center, has the S configuration by applying the steps, those 3 steps in order. Now let's look at when this becomes a little bit more challenging. When the groups attached to a chirality center are similar, it can be tricky to prioritize them. So we want to analyze the atomic numbers 1 layer of atoms at a time. So for example, if we're looking at this chiral carbon, it's clear that the oxygen will be the atom with the highest priority and the hydrogen will be the atom with the lowest priority. But these two are carbons and they have the same atomic number, so that's a tie. So then we look and see, okay, what is attached to these carbons? What is attached to this carbon is another carbon and 2 hydrogens. Same thing with the one on the left. We have a carbon and 2 hydrogens attached. So that's a tie. So then we move to the next atom attached. Over here on the right, we have a carbon that has, again, 1 carbon and 2 hydrogens attached. Whereas on the left, I've reached a carbon that's attached to 2 carbons and 1 hydrogen. Well, the carbon and carbon is a tie. Carbon beats hydrogen, and that's the tiebreaker. And you order these in order of atomic number from highest to lowest, which is why they wrote carbon, carbon, hydrogen, as opposed to, for example, carbon, hydrogen, carbon, or hydrogen, carbon, carbon. And so we were looking for the first tiebreaker, right? And the one with the higher atomic number gets priority. So as a result, the group here on the left is priority 2, and the group here on the right is priority 3. So this has helped us with a more complicated structure be able to identify the priorities 1, 2, 3, and 4, which is step 1 of the process. Here are some other examples where it might be a little bit confusing to figure out what has priority. So again, when you are looking at 2 atoms where there's a tie, carbon versus carbon, and we look and see what's attached to those carbons, we're going to place the atoms directly attached to those carbons in order from highest to lowest atomic number. So this carbon is attached to 3 carbons, that's all identical, so you just write carbon, carbon, carbon. But on the left, this carbon is attached to an oxygen and 2 hydrogens. So we would line that up, oxygen, hydrogen, hydrogen. And we look for the first difference, and that will be the tiebreaker. So again, the priority is based on the first point of difference. Oxygen has a higher atomic number than carbon, and therefore the group on the left is assigned priority 2, and the group on the right is assigned priority 3. When there's a double bond or a triple bond, that atom is said to be attached to whatever it's bonded to more than once. So it essentially counts twice. So for example, if we were trying to figure out what this carbon is attached to, we would write oxygen, oxygen, hydrogen. Okay, so that's step 1, and that should pretty much go through most of the confusing examples of how to assign priority 1, 2, 3, and 4. Remember that once you've assigned priority 1, 2, 3, and 4, by the way, a helpful hint is erasing it like the structure or redrawing it. And instead of drawing in like the oxygen or the carbon group, we can just change it to 1, 2, 3, and 4, right? By keeping the groups that are in the plane, and keeping the group that's on a wedge the same and on a dash the same, we can just write in 1, 2, 3, and 4. That's a little helpful hint instead of recopying the molecule by drawing the whole thing. Okay, so let's look at what would happen if we switch two groups. So if you switch, for example, this 1 and this 4, notice that the 1 was on a wedge and the 4 was on a dash. You switch it to the 4 being on the wedge and the 1 on the dash, you have switched the chirality center. So if this one is counterclockwise in S from 1 to 2 to 3, then when you switch two groups, it will be R. So that's something that's very helpful because let's say your fourth priority group was not where we want it to be, which is on a dash. You could switch two groups, noting that you've switched the designation while doing so, and then figure out the designation and go back. So for example, let's say I was given a compound with this configuration where my fourth priority group was pointed out at, coming out at me instead of going back where I want it. I could switch those two groups so that it looks like this. When I do that, I figure out that the fourth priority group is now back. That's great. So I can easily do 1 to 2 to 3 and come up with counterclockwise in S. Right? And so then this one was S, but because the original molecule had the 1 and 4 at different positions, the original molecule is R. That's a little hint or trick that you can use to help you figure it out without having to like visually flip over the entire molecule. Okay, so you can use that trick doubly so in order to go from the original configuration to the switched configuration and back to the original configuration. So for example, let's say we were given a structure and we've assigned the 4 priorities and it ends up looking like this. So this is currently not ideal because remember that I want my fourth priority group to be pointed back. It's only when my fourth priority group is pointed back that I'm able to figure out if I have a clockwise or counterclockwise rotation. So I think to myself, my fourth priority group is currently in the plane, but I want it pointed back. So I'll just switch it with whatever group is pointed back. I can do that, but in so doing, I've switched the designation, whatever it happens to be, either R or S, to the opposite designation. If I don't want to have to remember that I need to go back to the original designation, I can switch the other two groups to come up with this structure, which will have the identical configuration to the first structure. So again, by switching two groups, I've switched either from R to S or from S to R. But if I also switch the other two groups, then I'm back to the original either R or S, whatever it happened to be. And we could actually figure it out from here, right? Because we did some very important switches. We switched the fourth priority back to the back where we want it. And then we also switched 1 and 2 so that whatever configuration this is will be identical to the first. So if I go from 1 to 2 to 3, notice that I am doing a clockwise rotation with my fourth priority group pointed back. And so this is R, which means that the original structure was also R. That's another trick. So there's lots of different tricks on how to do it if that fourth priority group is not given to you in the back where you want it to be. This is just a summary slide talking about the different steps in assigning R and S configurations using the Cahn-Ingold Prelog rules. Again, we're going to identify the 4 atoms directly attached to a chirality center. Assign them a priority number from 1 to 4 based on highest atomic number, using tiebreakers as necessary. So this is the start where it looks like if you have a tiebreaker, then you have to keep going until you find a point of difference. Then once you have all 4 groups prioritized, 1, 2, 3, and 4, you need to rotate the molecule or switch groups so that the fourth priority is on a dash or going behind the plane of the page. With it in that orientation, you can determine whether the sequence 1 to 2 to 3 follows a clockwise order or a counterclockwise order to designate R and S respectively. Let's go ahead and practice. Try to assign the configuration of the chiral center in the following compound. Go ahead and pause it and then resume when you're ready to go over the question. Okay, so we're looking at this carbon is the chirality center. Sometimes it's helpful to go ahead and draw in the hydrogen attached to that carbon if it has not already been drawn in for you. Because this amine group is pointed back, I know that the hydrogen that's not drawn in is pointed out at me on a wedge. So the first step says to use atomic numbers to figure out the priority groups 1, 2, 3, and 4, which is based on atomic number. So nitrogen has the highest atomic number because it's nitrogen, hydrogen, carbon, carbon, right? Some people might get really distracted by how many oxygens are over here. But remember, we analyze one layer at a time, meaning we first look at exactly what's attached to this carbon. And exactly what's attached is nitrogen, hydrogen, carbon, carbon. Between those four, nitrogen has the highest atomic number. Hydrogen will definitely have the lowest atomic number. And this carbon and this carbon are both carbon, so that's a tie. But when I look and see that this carbon is attached to oxygen, 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 versus over here we have carbon, hydrogen, hydrogen, this is definitely going to be priority 2, which makes this priority 3 by default. From here, we can just figure out where is our fourth priority group. So we're done with step 1. We've assigned the 4 priority numbers. Now we need to use one of those strategies or tricks to get to make sure that our fourth priority group is pointed away from us. Currently it's pointed out, which is not what we want. So there's a couple of different ways that you could do this. The easiest way is a way that I really haven't told you yet, which is to look at this and say, this is 1 to 2 to 3 in a clockwise rotation, which is R. But because my fourth priority group is pointed out instead of pointed back, it's really going to be S. So basically, if your fourth priority group is not pointed back and instead is pointed out at you, you can just flip the designation because it's like you're looking at the molecule from the wrong direction. It's like you're looking at it instead of from the direction that you want with the hydrogen pointed back, you're looking at it from the other side with the hydrogen in front. So for me, if I go like this, that's clockwise, right? But for you, it's if you're looking from the other perspective, that would be counterclockwise. Okay, so you could just say 1 to 2 to 3 with the hydrogen coming out at me instead of going back, right? Instead of R, clockwise and R, it's going to be S. But let's look at some of the other strategies as well to see, like, let's say you don't follow my logic there. You want to use a different trick. Let's go ahead and work on those as well. So what I can do is just recopy this. And keep it looking as closely as you can with the 2 groups here in the plane, the one that's coming out at you and the one that's going back, like so. Right? And then you can just simplify this to 1, 2, 3, and 4. Right? So this could be simplified as 1, 2, 3, 4. So again, our first priority group is pointed out at us. So maybe you want to switch those 2 groups. Now you might be asking, why did I switch these 2 as opposed to another 2, right? Well, remember that my goal is to get the fourth priority group in back. So I want to switch the fourth priority group with whatever is currently in back so that my fourth priority group will be in back after the switch. All right, so that's why I'm switching those two. And then let's draw that. So we've done that switch. Right, and then we're going to draw it again. We're just going to keep everything exactly where it was. Don't change any of the wedges or dashes placement. Just change. Now this is going to be 1, and this is going to be 4 because I switched those two. And this is going to stay the same. I only did that because I just decided to switch these two. So again, at this point, you could figure out if this is clockwise or counterclockwise because my fourth priority group's in the back. And whatever this is, the original one was the opposite, right? So for example, if I wanted to just switch those two, I could do that. And I would go from 1 to 2 to 3. Notice that I started on 1, I went up to 2, and then I went over to 3. This was a clockwise and R, right, designation. And if this is an R, and I switch two groups, that means the original was an S. So let's say I didn't want to do that. I didn't want to remember to switch it. What else could I have also done, right? Maybe I also switched 2 and 3, right? So we'll kind of do, I'll redraw this over here. This is strategy 1, right? So again, R became S, the strategy. What is another strategy? The other strategy, again, I'm just going to copy this over because this was my original. Is to switch the fourth priority group with whatever is in the back and simultaneously switch the other two groups. Right, so this is now 2 switches. Right, and so now I have 1 over here, 4 over here, and I've also switched 2 and 3. So because I've done 2 switches now, I can still do 1 to 2 to 3, 1 to 2 to 3. Right, now this is a counterclockwise and S configuration. Because I switched 2 sets of groups, it's now still the original S. Right, so that's one strategy. Here's another strategy. Or you could just remember that if my fourth priority group is pointed out at me instead of pointed back, when I do a clockwise rotation from 1 to 2 to 3, instead of R, it's going to be S. So 3 different ways that you could do it. You could also flip the molecule over. You could draw a Newman projection down the carbon-hydrogen bond. There's a variety of ways to do it, but these are the main ways. Okay, so again, the designation of the chiral center as R and S is an important part of the IUPAC name for a compound when you have a chiral compound, and it's important to be able to distinguish it from its enantiomer. So for example, don't really worry about necessarily how to name this because we haven't learned how to name alcohols yet, right? But you could do this with alkanes, which you do know how to name, and make sure to include the R or the S in the name. And it goes in brackets in front of the entire name. So either R or S. It doesn't have to be in red. That's just to sort of highlight it for you. And then let's say there's 2 chiral centers, right? So then you want to list each one as either being R or S. Because there's more than one, now you need the carbon number on the parent. So you don't have to know exactly how to name this. But just believe me that it gets named 1, 2, 3, 4, 5. So then carbon number 2 and carbon number 3 are chiral centers. So I'll list the configuration of 2 first with the 2 in front of it. So this is R, so it becomes 2R. And this is S, so it becomes comma 3S. And if there were more, you would just keep listing them in number order, like 2R, 3S, 4S, 5R, and so on. So it's an important part of the name because without it, you can't know what the true structure is in terms of its 3D nature. Okay, again, there's lots more to this chapter, but we're going to stop here for the day and you can start working on the activity.